Hello everybody. Let's talk about complex numbers. My name is Ricardo. I'm professor at the Physics Institute of the Federal University of Goiás. So, consider this general form of a quadratic equation of a certain unknown variable z. So, az squared plus bz plus c equal to 0. A, b, and c are coefficients, real coefficients. The well-known solution for the unknown z is given by this expression here. This term inside the square root is called discriminant. So in case the discriminant is non-negative, in other words, b squared minus 4ac greater than or equal to 0, then we have real solutions. The solutions are real numbers. But in case the discriminant is negative, then we need to introduce a new kind of number called imaginary number. And this is a definition: I is the square root of minus 1. So the imaginary number, or sometimes called the unit imaginary number I, is defined as this, which is the same as I squared being equal to minus 1. So if we allow I to be multiplied by a real number, then we obtain imaginary numbers of the form bi, where b is a real number. For instance, 2i. 2 is a real number multiplying by I, so we have imaginary number, another imaginary number. And if the multiplication rules are extended to imaginary numbers, then the product of imaginary numbers is a real number. This is the main example. We have the product of two imaginary numbers and the result is a real number. So I being multiplied by I is I squared and it is equal to minus 1. Another example, 2i, which is an imaginary number, multiplied by 3i, another imaginary number. So the result is going to be I squared is minus 1. 2 times 3, 6, so the result is minus 6. More examples. So the square root of minus 4, the square root of minus 1 is I. So here we have the square root of 4 times I, which is 2 times I. So we have imaginary number here. Another example, I squared multiplied by I. So we have I to the third power. This, since I squared is a real number, so we have here an imaginary number I multiplying a real number, which is minus I. So these two examples are imaginary numbers. But if we multiply two imaginary numbers, such as this example that we already discussed, this is minus 1, which is a real number. Another example, the square root of minus 2 multiplied by the square root of minus 3. This is an imaginary number, and this is another imaginary number. So the square root of minus 2 can be written as the square root of 2 multiplied by I. The same for this number here, which could be written as the square root of 3 multiplied by I. I squared is minus 1, and the product of these two roots here is the square root of 6 with this minus sign. So these are two examples of real numbers. The product of imaginary numbers resulted in real numbers. we can perform multiplication and division among real and imaginary numbers. Okay, we can do that. We saw a couple of examples. And which results in an imaginary number. Okay. But can we perform addition among real and imaginary numbers? Can we add a real number to an imaginary number? Well, we can, but we are going to present complex numbers. Complex numbers are a combination of real and imaginary number. Let's talk about this now. So a complex number z can be expressed by the general form z being equal to x plus I multiplied by y, where x and y are reals. So x is the real part of z, and y is the imaginary part of z. So z has two parts, and this is the real number, and this is an imaginary number. But we call x as the real part of z and y the imaginary part of z. Another terminology, so we can say that x is the real part of z and y is the imaginary part of z. So, do you mean that the imaginary part of z is real? I mean, the imaginary part of z is not imaginary? Yes, exactly. The imaginary part of z is y, which is real. So, we can see z written as with using these terms here, the real part of z and plus the I multiplying the imaginary part of z. So in case y is 0, then z is a pure real number. Pure real number. And in case x is equal to 0, then z is a pure imaginary number. Okay, so now we can perform addition, subtraction, multiplication, and division on the complex numbers. They have all the desired algebraic properties and represent an extension of the real number system. The term complex number means any number in the whole set of real numbers, imaginary numbers, or the combination of them. Examples: 1 plus I. This is a real number being with this term I, which is imaginary, and there is an addition between these two numbers. 5i, which is an imaginary number, so this is also a complex number. 16, which is a real number and is a complex number. And this another combination, another addition example of a real and an imaginary number. So all these are examples of complex numbers. Equality of two complex numbers. So if z1, certain complex number, z1, is equal to z2, this means that x1 is equal to x2. In other words, the real part of z1 is equal to the real part of z2. And y1 is equal to y2. The imaginary part of z1, which is y1, is equal to the imaginary part of z2, which is y2. And vice versa. So, if x1 is equal to x2 and y1 is equal to y2, then z1 is equal to z2. The complex numbers, the two complex numbers are equal. Another form to see that is to write z1 as x1 plus I y1 equal to x2 plus I y2. So to have this equality, x1 should be equal to x2 and y1 equal to y2. Now, some basic algebra. The addition. So consider this complex number, a1 plus I b1 plus another complex number, a2 plus I b2. The result of this operation is we will sum the real parts, which is a1 plus a2, plus the imaginary part. So I multiplying b1 and b2. So b1 plus b2 being multiplied by I. This is the real part of the resulting complex number, and this is the imaginary part of the resulting complex number. Multiplication. If we multiply these two complex numbers here, then we will have a1 multiplying a2, and we will have this term here multiplied by this one here, which results in I squared, which is minus 1, b1 times b2. And we have to consider the crossed terms. So a1 multiplying ib2 and ib1 multiplying a2, which is a1 b2, so a1 b2, and plus a2 multiplying b1. This is another complex number. The real part is this one, and the imaginary part is this one. Subtraction. So in case we want to subtract this complex number by this another one. So let's consider this as another resulting complex number, x plus iy, and now we can add on both sides of the equation, we can add this complex number here. So when we add that on the left side of the equation, this term will vanish, will cancel to the term that we are adding, and the result is a1 plus ib1. And in the other side, we will have x plus iy plus the term that we added, a2 plus ib2. Now we know how to add, so we know now that a1 is equal to x plus a2. So x is going to be a1 minus a2. And we know that b1 is going to be y plus b2. So y is going to be b1 minus b2. Okay, we could do that, for instance, multiplying this complex number by minus 1, and then we obtain the subtraction form, and we can proceed the same as we did for the addition. Division. So consider the division of these two complex numbers, and we will solve that multiplying by c minus id and dividing by c minus id as well. So if we do that, here we will have a times c plus I multiplying minus I squared is minus 1. But with this minus here, we'll have plus b multiplied by d. And the crossed terms is going to be a multiplying minus id and ib multiplying c. So ibc minus id. And here we have c squared and I being multiplied by minus I is plus 1. So we will have plus d squared. The crossed terms will cancel each other. Okay, now I can see that this term here divided by c squared plus d squared is going to be the real part of the resulting complex number. And the imaginary part is going to be this divided by this guy here. Okay, so the result is another complex number, where, of course, c squared plus d squared is different from 0. Otherwise, we could not do the division. Representation. Okay, so note that the symbol I and the binomial relation a plus ib, which is the complex number, the representation of a complex number that we are using so far. So both the symbol I and the binomial relation are just conventions. They're not indispensable. It is possible to define a complex number as a pair of real numbers, such as A and B, a pair of real numbers, obeying certain particular rules. So this pair of real numbers, which is a complex number, must obey certain rules. For instance, the multiplication of two complex numbers. We know how to proceed with the multiplication considering this representation we did in the previous slide. So the multiplication can be defined by using this representation here. We have this complex number, which is a pair of two real numbers, a1 and b1, multiplying another complex number, which is another pair of two other real numbers. So we must define the rule of multiplication such as this. The result is another complex number, which is a pair of two real numbers. The first one is given by this expression, and the second real number is given by this expression. So if we define this rule of multiplication, we can use the representation of a pair of two real numbers to express a complex number. So the idea here is to say that the form a plus ib is just a representation of a complex number. Just a representation. We could use a different representation. So the question now is there any other representation of a complex number? So let's first talk about the complex conjugate of z, the complex conjugate of a complex number. So consider z, an example of a complex number, which is equal to x plus iy. Then we can define z star, the complex conjugate of z, as x minus iy. So instead of plus, minus iy. So this is the complex conjugate of z. And to emphasize, this is just a definition. So from the definition, if we do the multiplication of z star by z, or z and z star, doesn't matter the order here. If we do this multiplication, we will have x minus iy multiplying x plus iy. The result is going to be x squared, and we will have here minus I squared, y squared. The crossed terms is going to cancel each other. And I squared, we know that it is minus 1, so the result is x squared plus y squared. So the product of a complex number by its complex conjugate is a real number. Again, the product of a complex number by its complex conjugate is a real number. Okay, this is very useful, many applications, but I will use this to show another representation, a very useful representation. From this result, from the previous slide, we can create a very useful representation based on the Pythagorean theorem, which is the geometric representation or trigonometric representation. So consider these two axes. The horizontal one is the real axis, and this vertical one is the imaginary axis. And consider this point P, which is a representative point describing a complex number Z. So the location of this point is describes a complex number Z. So the coordinate in this axis is x, and this y is the coordinate of this point in this axis. So the complex number, we can see from this, can be described by these two coordinates, one in the real axis and this other one in the imaginary axis. But the location of this point can also be described using polar coordinates, r and theta, the angle theta, with regard to the real axis. And the relation between x and y with r and theta is given by x is given by r cosine of theta, y is given by r sine of theta, and we know that r squared is x squared by plus y squared. We can obtain theta using these two expressions here. So we know that a complex number is given by x plus iy. So we can also write it in terms of r and theta. So z is going to be r cosine of theta plus I times r sine of theta. So if we write it such as r multiplying this term here, we can also see that this term, using the Euler's formula, can be written as the exponential of I theta. So this is another form to express a complex number using polar coordinates, and we used this trigonometric representation of a complex number. So the complex conjugate of z star, is given by r cosine theta minus I sine of theta. So we just change the sign, instead of plus, minus sign in the imaginary part. So using this result, we can see easily that z star multiplied by z, the product of a complex number z by its complex conjugate z star, is equal to r squared. So you will have r squared here, and then you will have multiplying these two guys here, cosine squared of theta plus I squared is minus 1, with this minus gives plus. So you will have cosine squared of theta plus sine squared of theta. The cross terms will cancel each other. the result is the product is r squared. That's why we call that, based on the Pythagorean theorem, we can use this representation, this geometric representation of a complex number. And we can also write it as r multiplying exponential of I theta. So the complex conjugate of z is given by this term here, which could be written as r multiplying exponential of minus I theta. And again, if we use this form of the complex number to multiply, to obtain this guy, this is much more easy than the previous one that we performed. So, an exercise. Consider the real axis and this imaginary axis, and we have a certain point P, which the location of it expresses a complex number, z. But then I'm just writing that this point here, the location of it, expresses the complex number z. And the real part of this number is 1, and the imaginary part of it is the square root of 3. So, from this, I can write the complex number using this representation, this form, as z is equal to 1 plus the square root of 3 multiplying I. Okay, but we also can use polar coordinates, r and theta. So in this case, I need to find who is r and theta. So r squared is given by x squared plus y squared. I know that x is 1 and y is this square root here. So the result of this is going to be 1 plus 3, which is 4. And then r is equal to 2. X is given by r multiplying cosine of theta. So the cosine of theta is going to be x divided by r. Since x is 1 and r is 2, the cosine of theta is going to be 1 over 2, which gives us that the theta is going to be pi over 3. So, using this form, this representation for z, we can write that first this one, then we will do using this form here, using the Euler's formula. R is 2 and theta is pi over 3. So this is a form to express a complex number. But there is a simple form using the Euler's formula here. So in this case, the complex number z is just given by 2 multiplying the exponential of I p over 3. So, in other words, 1 plus square root of 3 multiplied by I is equal to this guy here. These are two different representations of the same complex number. So, this is just an example of application of complex numbers. Consider these two complex differential equations. So in the study of quantum mechanics, even non-relativistic quantum mechanics or relativistic quantum mechanics, we will deal with equations such as this one, which is a differential equation, but not only that. This is a complex equation. You can see this here. This is the Schrödinger equation. And we have here the Dirac equation, also a complex equation. So in the study of complex mechanics, in the study of quantum mechanics, we deal with complex equations in complex quantities. So this is an example of application of the study that we just performed about complex numbers. The derivation of this equation here was is given in this video, which is in our channel. Thank you very much.